thing. Okay. So when you're implementing this in practice, you optimize over measures. You uh, so I mean, optimizing over measures is too hard. So you optimize over linear functionals, and you get some pseudo moments, some pseudo moment sequences up to degree d. And then the question is, how do you get the function y out of that? And there's an answer. It's a separate story that's very nice. It's called the Christoffel function. So it's a way to understand where the measure the measure mu is concentrated its support uh, if you only know the moments of the measure. So that's what you can do. You can use the Christoffel function to get the measure back. And then the support of mu, which you get through the Christoffel function, it gives you an approximate solution to your PDE problem. Okay, so to recap, we start with a classical problem where we're minimizing over the Lipschitz functions, y. We relax it. So now we're minimizing over the occupation measures. Well, these pairs of a measure encoding the bulk and the measure encoding the boundary. And of course, the relaxations, this is a bigger space. So we always have that the second is smaller than the first, right? In fact, every Lipschitz function induces an occupation measure. So you can say that the first set is contained in the second. So you have this relation, and so the question would be, are we actually getting to the right answer if we go through the second problem? Are we actually getting the answer to the first one, right? Do we always have that these two things are the same? And this was the problem that Milan and I tried to solve first. And okay, so of course there are some certain situations in which it's easy to see that you have gaps. So a gap means that the relaxed one is smaller than the classical one, and so I'm not going to stop and bore you with all the details here. But if you have something that on the derivatives, a Lagrangian that on the derivatives is not convex, it's very easy in this kind of situation to find examples. And the better example I recommend to you is given by Fantuzzi and Tobasco. But this example here, it also works, and it's just not so nice because you need a kind of absurd constraint that y be equal to 0, which means that there's only one solution, y equal to 0. Okay, but with less constraints, you can go and look at Fantuzzi and Tobasco. So the question is, okay, are these two things the same? And for the one-dimensional case, so when omega is just an interval, this had been studied a lot, and in fact, we already knew that you have no gap. The classical and the relaxed answers, they are the same. So there were also some other partial answers for the higher dimensional cases, given these other works. And let me just go a little quicker. And so the result we found with Milan is this, that if you have now a Lagrangian that is quite so I mean, you have some hypotheses. I'm not listing everything here, but they are really mild. It's basically that L, the Lagrangian that we're integrating, should be convex in the last variable in the derivative, and locally bounded and measurable. Then we get that if the codomain y or the domain are of dimension 1, then there is no gap. But in all other cases, there is a gap for some examples. Okay, I'm not saying that for every L there's going to be a gap, but we have examples where there are gaps, right? And more recently, we found a very nice sufficient condition to have no gap in any dimension, together with Didier Henrion and of course Martin, who is here. And so that's what we have for now. And we also treated the optimal control case, and it turns out that if you have integral constraints like this, then we also have gaps, and so I guess I wanted to explain to you a little bit what the proof looks like. But yes,
Just a small question, maybe a stupid.
please, yes.
Just in a normal hierarchy, normally there is some conditions on the domain which are the compactness and this Archimedean condition,
Yes.
right? For the to have this.
Right. Okay. So the thing is, these results here, they are previous to turning the thing into sum of squares, to going into that scheme. This is more of an analytical result. You see, this is we're still just with a domain in a RAN, and so we, in fact, it's, if you want, it's more general, because we're not even asking omega to be semi-algebraic. It's just open, right? So in a sense, it's, yeah, it's, these results are more general like that. But well, I wanted to talk about the sums of squares and all that, because it's right there that you see their relevance, right? Because if you don't have equality, then the algorithm, you would say, maybe it's worthless. But I want to tell you also why I think even when you have a gap, the phenomena we've seen tell you that the algorithm finds the better solution. Okay. So if let me just say quickly how to get the first result of equality here. So what's happening is you have your sets omega and y, and here you have some mass, right? And you want to somehow say, okay, yes, this is the same as minimizing over some Lipschitz functions that look reasonably nice, right? In fact, how do you turn it into maybe one of them, right? A single Lipschitz function, right? So it's a little mysterious. So what we found is that, in fact, this mu, you can decompose it into a superposition of measures that are induced by Lipschitz functions. And once you do that, the extreme points of the superposition, I mean I mean, a superposition that minimizes each of its of the points that it's superposing minimizes as well, because of convexity. I guess it's the converse to the Choquet theorem. And so, since the functional mu going to the integral is actually linear, the extrema are attained at the extreme points, and so you get a Lipschitz function, and so you get the opposite inequality that you wanted to get. But how to say this? The hard part is the first step, right? How do you decompose that? And so it's like this. Okay, so imagine you're looking for some sheets phi 1, phi 2, phi 3, such that somehow, you know, maybe like if I go up, if I go on a vertical line, I go up and up and up. I am kind of accumulating more and more mass as I move up, right? And so somehow I should, I mean, there's this idea of, can I somehow define a function whose vertical derivative, who's such that the level sets give you the boundaries of the level sets are these sheets that you're looking for, and so somehow what you would want is some relation like this, like the vertical derivative would be mu, right? And can you make that work? And so you start reasoning in terms of weak derivatives, and so imagine you have some sort of test function that looks like an integral of phi. So integral of phi is like a test function, and your imagine mu where rho times dx, right? And then so you integrate by parts, and you would have that thing on the right, because of the fundamental theorem of calculus. The integral would cancel out with the derivative, and so this works. As it turns out, this works. You define this functional, which is basically going to give you rho using the Radon-Nikodym theorem, and this is a wonderful idea that was developed by Hadpitz and Svorsky, and they wrote it in a very strange way, but we managed to generalize it and get it to this situation that is now the result we have. So once you have that thing, that rho, it turns out to be a function of bounded variation, which means that it satisfies this kind of condition, and by the coarea formula, its sublevel sets are of, this is called finite perimeter, which finite perimeter means that they satisfy this other condition. And then so we need to show that this boundary sets of the levels, of the level sets, they are actually Lipschitz functions, and de Giorgi already proved it. So so there's his structure theorem that gives on the boundary an exterior unit normal that with the Hausdorff measure of the boundary, it gives basically the Gauss-Green formula. Okay, and so that's what gives. I mean, this is what proves then that the boundaries of the level sets are Lipschitz functions, and so you have your decomposition, and so we have this equality, and then the examples for the other dimensions, they I'm not going to bore you with all of that, but yeah, so this is the second part. I mean, yeah, I mean, so there's the examples, they look like the Riemann surface of a square root. I don't know. Okay, maybe we let me just say, okay, it's a little complicated, but so we have this general principle that going from a PDE variational control problem, we can actually do a hierarchy of tractable semi-definite programs, get the solution, and then we know that the solution is the right one in all those cases. And so what I just wanted to say is, in our examples, what we found is that the right solution is kind of a function with two values. You see, so here you have, for each point on the disk, you have two values above. So sorry, it looks more like this, right? It doesn't really self-intersect because it's in R4 in four-dimensional space. So this doesn't really self-intersect, but so the example looks a little like that. And the thing is, every time you have some function that tries to minimize this problem that we use for our example, the function needs to jump. Okay, and so in that sense, the two-valued solution is, in my view, is the right answer to the problem. right? Because it doesn't need to jump. And so my view is that sometimes this um, uh, sometimes measure valued solutions are really the right answer for some applications. And so I think even though there may be a gap between the relaxation and the classical problem, uh, it's I mean the algorithm is still very valuable because it gives you what I think is the right solution. But okay, of course this is controversial and it depends on the application. But I just want to say also that we also found this, as I had said before, this sufficient condition for there to be no gap, and it's even true. Well, in a more general case, when we use so-called finely relaxed occupation measures, something else, we have the optimal case, optimal control case. We have all sorts of constraints, and we have a very nice application to micromagnetics that was brought about by Martin. And I just want to say the way the proof works is, so now we assume that L is simultaneously convex in y and z. So before it was just convex in the derivative variable. Now we also have convexity on y. And as it turns out, if you define a function y that is going to be the average of the positions of the measure at each, so you fix x and then you get the average at y of y's. It turns out that the Stokes condition we had talked about before, it gives you, it tells you that the average of the positions of z is actually going to be the weak derivative of y. And so of course there are technicalities, but using this you can then apply Jensen's inequality to get the final result there. And so I mean, of course there are many other technicalities in the middle, and I'm oversimplifying, but that's how you get that result. And so thank you very much. Right. Okay. Are there other questions? No?
Are there any questions? We have the
No?
microphone.
Thank you for the nice talk, and I would like to ask if the algorithm is implemented as a software library that we could use, or
It's implemented, but it's not. I mean, it's still in research level. So I mean, there are some examples, but basically for each example you need an expert. Still, it's not. I mean, it's very recent, and there was this result missing about the gap that was not, I guess, making it hard to convince people that this was worthwhile. So yeah, it's in development, in a sense.
Any further questions?
Mm-hmm.
Well, thank you. And maybe I can just shout.
No, it wouldn't be on the recording.
Okay. Just I think I remember that in integer optimization, like in discrete optimization, there were some types of relaxation that gives you a guarantee about how far away the gap, like how far away is the relaxed solution to the original solution. I think there's something like 0.8 thing in. Well, I don't remember the. But well, the idea is just, do we have an estimation about the gap?
No, not in this case. I don't know about the case you're talking about, but no. Yeah. Oh, it's a good question. Yeah.
Any further questions?
No. Okay.
Extensions to non-commutative problems? Cool. So let's thank Rodolfo once again.
Okay. Thank you very much for being here.
Thanks so much for coming.
Yep.